Okay, thank you everybody for attending my presentation. Actually, today, during the COVID-19 pandemic, we all had a different schedule and behavior in our buildings. However, all our buildings have been operated the same as always. So it brings out the question that as the behavior of the people is always varying over the day, should the operation of the building be the same or it should be adaptive to the behavior of the people? To answer this question, we first see how we can give a learning ability to the buildings so they can adapt to the operation, to the behavior of the people. Then we will see what would be the potential benefits by looking at some examples. And finally, we will talk about the case study of self-learning hot water production systems. So in this presentation, I will give a brief introduction into the reinforcement learning, which is a method of machine learning that can be used to provide the learning ability to the building energy systems. Then we will talk about a few examples where reinforcement learning is actually implemented on different systems of the buildings. And we will talk about the first step of our research, where we implemented reinforcement learning for developing occupant-centric hot water production. And finally, we will have a very brief glance into the future steps of our research. So today, many new components are added to the building energy system, such as heat pumps with variable COP, electric vehicles, renewable energy, and so on, that increase the complexity of optimal energy management in the buildings. So today, when we are going to develop a control logic for the building energy system, several questions come into our mind. For example, how should I schedule the space heating so that I pay less for electricity? How to get maximum use of solar energy with my hot water tank? How to use my electric car as a battery for PV, and so on. However, it is not easy to answer such questions because, for example, the renewable energy is volatile and it is sometimes hard to predict. The heat pump COP is variable over the day because of the variations of the water temperature and tank temperature. The electricity price also can be variable based on the tariffs that they can have. The hot water demand, for example, is highly stochastic, and so on and so forth. But should we always explicitly program the control logic of the buildings and tell them exactly what to do? Or rather, we can give them the learning ability and let them to learn by themselves how to operate the energy system in an optimal way. As humans, we are always learning from our experiences. Then we change and adapt our behavior to the environment that we live in. And also we try to maximize a goal in our life. So inspired by humans, the buildings also can learn from their experiences. And the experience for the buildings can be the previous control actions that they do and the consequences of those actions. The buildings also can change and adapt their behavior to the environment that they are in. And for example, as the buildings, they can adapt their behavior to the sources of uncertainty. For example, the renewable energy, occupant behavior, weather condition, and so on. And the buildings also can try to maximize a goal over the operations of over their operational life. For example, the buildings can also try to maximize the energy saving while keeping the comfort for the occupants. So reinforcement learning is a method of machine learning that can provide the learning ability to the buildings. In reinforcement learning, we have a controller which is known as agent in the literature of reinforcement learning. Then we have an energy device to be controlled, which is known as environment. The agent first observes the current state of the environment. And this state is basically a vector containing different parameters that describe the current condition of the energy device. For example, temperatures, pressures, and so on. Based on the observed states, the agent will then perform an action on the environment. And this action can be, for example, turning on or off the energy device. And based on this action, the energy device will therefore transit to the next stage. And based on how good is the performed action, the agent can be rewarded with a predefined function that this reward basically quantifies how good was the performed action and how good is the new state of the environment. So this loop of state, action, and reward is repeated again and again until the agent learns that at each specific state, what action to perform to maximize this predefined reward. So when it comes to machine learning, people usually think about the supervised learning. In supervised learning, we have a labeled data set of the system, and we train our model based on this labeled data set. However, in practice, we usually do not have a labeled data set with enough data to train our model. And also, we do not even have an accurate model of the system to generate some data that we can use to train our model. But on the other hand, reinforcement learning do not need a prior data set because it can learn and adapt to the specifications of each new building only with interacting with that building. So this makes reinforcement learning a very practical method among other machine learning models. Among different alternative control methods that are currently developed, model predictive control is probably one of the most promising methods. Model predictive control has shown a good performance in theory, but when it comes to practice, it has some limitations. It has some drawbacks that limit the widespread implementation of model predictive control, especially in the building sector. First of all, model predictive control is a model-based method, so there is a lot of time and effort required to develop an accurate model of the building. And even if we develop an accurate model of the building, this model can become inaccurate due to some changes that can happen during the operation of the building, such as, for example, renovation of the building. And because it is based on a model, it is not easy to transfer model predictive control into many other buildings. And model predictive control is basically optimizing a model of the system at each time step to select the best optimal action. So it is quite computationally expensive and it cannot be implemented on a cheap hardware. Also, model predictive control is quite rigid to the changes because if there are some changes in the operation of the system that has not been expected during the development of the model, then model predictive control cannot adapt to those changes and will continue to unoptimally control the building. On the other hand, reinforcement learning has two main advantages. First of all, it is model-free. Therefore, there is no time and effort required to develop an accurate model of the system. And because it is model-free, it is easy to transfer it to many other buildings. And also, when the reinforcement learning model is trained, then it is computationally efficient and it can be deployed on a cheap hardware such as Raspberry Pi also. And reinforcement learning is adaptive, which is another major benefit of reinforcement learning. It means that if there are some changes during the operation of the system, such as a change in the human behavior, in the weather conditions, renewable energy potential, or so on, the reinforcement learning can always learn and adapt to these changes and always keep an optimal operation for the system. Here, I wouldn't go into the theoretical details of the reinforcement learning, but I should point out that reinforcement learning is not one single algorithm. There are several algorithms developed for reinforcement learning. These algorithms can be divided into the value-based and policy-based methods. Value-based methods are mainly for the discrete actions, and policy-based methods are for the continuous actions. Then to each of these groups, a model of the system can be integrated, which makes the subgroup of model-based reinforcement learning. But we should note that a major advantage of reinforcement learning is to be model-free. So if we have a model of the system, then there are better ways, such as model predictive control that we can use. One of the most commonly used methods of reinforcement learning is the deep Q learning. In simple words, in deep Q learning, we have a neural network that takes as the input the different parameters of the state of the environment, and as the output, it calculates the value the expected value of performing each of the predefined actions. Then the agent will perform the action which is expected to return the highest value. And the goal of the agent is to maximize the discounted summation of the rewards over entire episode. So reinforcement learning is a relatively new method, and therefore there are not many studies that have experimentally implemented reinforcement learning. In this presentation, I tried to include a few examples that have experimentally implemented reinforcement learning in real-world systems. And these studies include the implementation of reinforcement learning for coordinated management of thermal comfort and air quality, for the coordinated management of thermal comfort and electric vehicle, for operation of air handling units, and also for occupant-centric control of lighting in the buildings. For each of these studies, I will just quickly develop how the reinforcement learning framework is implemented. But if you are interested to read more about these studies, I have provided the reference below of the page. So the first example is about the application of reinforcement learning for the coordinated management of thermal comfort and air quality. In this framework, the agent is supposed to learn how to reduce the energy consumption of the building while keeping the thermal comfort and air quality inside of the building. The possible actions that the agent can perform to control the system is to select the temperature set points for the indoor air and also to turn on or off the ventilation fans. This study is implemented in a classroom in a university building, and the results show that reinforcement learning compared to the rule-based control could provide a higher PMV value while providing a 10% lower CO2 and also 4 to 5% lower energy consumption. The next example is about the application of reinforcement learning for operation of air handling units. In this example, the agent is supposed to learn how to provide a stable supply air temperature by, which is set by the occupants. And the possible actions that the agent can do in this system is to regulate the degree of the valve opening of the air handling unit. This study was implemented in a university building in Germany, and the experimental results show that the agent could successfully learn how to provide a stable supply air temperature by regulating the valve state. And also it is recommended in this research that the agent should be trained offline to make sure a fast convergence when it is implemented on the real system. So the next example is about the application of reinforcement learning for the occupant-centric operation of lighting in the building. In this example, the agent is supposed to learn how to optimally adapt the indoor lighting to the preferences of the occupants and environmental conditions. The possible actions for the agent in this study was to, of course, turn on or off the lighting in the building. And this study was experimentally implemented in 5 offices in the university building in United States. On the right side, I have provided a picture of the hardware that is used in this study. This hardware includes a light sensor, which is used to sense the current level of the light in the building. Then a Raspberry Pi Zero is used to for 2 purposes. The first purpose is to sense the occupancy of the building using the Bluetooth module. And also it is supposed to perform the actions which is selected by the agent on the cloud. And also a commercial device is used which enables both automatic and manual interaction with the lighting system. And the results of this study mentioned that compared to the occupancy-based and the schedule-based methods, the reinforcement learning method could provide a better balance between the occupant comfort and also the energy use. The final example is about the coordinated management of thermal comfort and electric vehicle in the buildings. In this example, the agent is supposed to learn how to adjust the indoor air temperature and how to schedule the charging of electric vehicle to reduce the electricity costs while responding the requirements of the occupants in the building. In this study, the possible actions for the agent was to adjust the state of the valve and also to charge the battery. This study was implemented in Nest building, which is in Empire in Switzerland. And in this building, a battery was used to emulate the operation of the electric vehicle. And the experimental results of this study shows that reinforcement learning compared to the rule-based control could provide about 30% of the energy saving, while maintaining a similar comfort as a rule-based control. So in our literature review, we observed that there are only few studies that have implemented reinforcement learning on the hot water systems. And also most of these studies have used a model-based reinforcement learning method. So in the first step of our research, we tried to evaluate the potential of model-free reinforcement learning to develop an occupant-centric control for the hot water production system. So in the following, I will discuss why occupant behavior is a key challenge for efficient hot water production, how water heating can learn and adapt to the occupant's behavior, and what would be the energy saving potential. The occupant behavior is already known as a key challenge for the optimal operation of different energy systems in the building, such as space heating, cooling, lighting, and so on. But when it comes to the hot water, it is even more challenging because the hot water use behavior of the people is highly stochastic. And we never know when the people are going to use hot water, how much they are going to use hot water, for what purpose they are going to use hot water, and so on. And also the hot water use behavior of the people can change from day to day, and also it can change from one building to another. And one of the reasons that the hot water use behavior can be different from one building to another is the family composition. Because if, for example, if we have two neighbor buildings with the same area and the same family size, and one of them has more number of children, they can have very different hot water use patterns. So we can say that each building is unique. Another challenge in the hot water system is that on the demand side, the occupants prefer maximum 40 Celsius degrees, which is when they are going to use, which is when they are going to take shower. But on the supply side, whenever we are going to keep hot water for a long time and in high volume, we need to maintain the temperature of the hot water above 60 Celsius degrees to make sure that that a bacteria called Legionella cannot grow in the water. So there is a mismatch basically between the supply and demand in the hot water systems. But there are two common approaches today to overcome these challenges. The first approach is that either we produce hot water in a high volume and high temperature, and we keep it in a storage tank to make sure that whenever the people need hot water, it is available in enough quantity. However, this method is quite energy intensive. The other approach is to use instantaneous water heating systems which produce hot water whenever it is demanded. In this approach, only the on-demand water heating systems can be used, which have a lower efficiency than the heat pump systems. So it is necessary to integrate the occupant behavior into the control of water heating systems. To this aim, in the first step of our research, we aim to develop a control framework that can learn the specific behavior of occupants in each building, then can continuously adapt the control strategy to the occupant's behavior, can make a balance between energy use, comfort, and hygiene to be model-free, which makes it easy to transfer to many other buildings, and also to be data efficient. So when it is implemented on the target house, it can quickly adapt to the behavior of that house. Reinforcement learning has shown a great potential in many different examples. One of the examples that is probably more related to the human behavior is the DeepMind, where reinforcement learning was playing a board game with a famous player of that game and successfully won that game. It shows that if reinforcement learning is set up properly and is trained properly, it can reach to a level that can learn and predict the decisions which are made by the humans. In our problem also, we can assume that reinforcement learning is supposed to play with the humans, with the occupants in the building. But in this example, the reinforcement learning is supposed to learn when and how much they use hot water and to produce hot water to reduce, somehow that reduce the energy consumption of the system. Here I have presented our control framework in a nutshell. In our framework, we have several stochastic parameters. We have outdoor air temperature and hot water tank temperature, which are varying over the day. Then, due to the variations of the air and tank temperature, the heat pump COP is also varying. And we have also Legionella bacteria, which has a complicated growth process. And on top of all of them, we have occupants, which have a very highly stochastic behavior. So in this framework, the agent observes the state of the environment. The state of the environment includes the current state and a look-back vector into the previous states. Then the agent can perform different actions. The actions that can perform in this example is is either to turn on or off the heat pump system. Then the agent will receive a reward. This reward includes three different terms containing the energy, comfort, and hygiene terms. Then this loop of state, action, and reward is repeated again and again until the agent learns at each specific action, at each specific state, what actions to perform to maximize this reward. So to monitor the real world behavior of hot water use behavior of the people, we used LoRaWAN-based IoT flow sensors, and we installed them on all of the water assets in the building. The monitoring campaign in our study was for 14 weeks, and it was from 28th of August up to 4th of December 2020. And as you see, it has been during the COVID-19 pandemic, and especially during the lockdown period where all of the occupants have been working from home. Therefore, they have a higher stochastic hot water use behavior because they are always in home and they can use hot water whenever they want. On the other side, it will further highlight the adaptation potential of the reinforcement learning to an abnormal situation such as COVID-19 pandemic. The proper setup of states and actions is very important to achieve a good performance in reinforcement learning. In our framework, the states include the air temperature, the water temperature, the hot water demand, and the power usage of the heat pump. And the actions are to turn on or off the heat pump system. The reward function also includes three different terms. The first term is the energy reward, which is penalizing the agent for any energy usage of the heat pump. The second term is the comfort reward, which penalizes the agent if the comfort temperature of the people is violated. And the third term is the hygiene reward, which penalizes the agent if the agent do not overheat the tank at least one time per day. And therefore, the agent is supposed to maximize the total reward, which is the weighted summation of all these different terms. Here, I would not go into the details of the training process, but I should point out that to ensure a fast convergence on the target house, and also to ensure about the comfort of the occupants, we first used a stochastic hot water use model to train our model offsite. Then we trained our model on the real hot water use data, which are collected from the case study buildings. These diagrams show the performance of the framework over 2 weeks of the deployment phase, where the agent is no longer learning, but only is controlling the hot water system. The first diagram shows the controlled signal versus the hot water demand. Also, the hot water use behavior of the occupants is highly stochastic, and it is further stochastic during the COVID-19 pandemic. But as we see in this diagram, the agent could successfully learn how to adapt the control signals to the hot water demand. For example, it is turning off the heat pump when no demand is expected to happen in near future. And also the temperature of the tank. In this diagram, I have shown the temperature of the tank versus the comfort temperature of 40 Celsius degrees and the disinfection temperature of 60 Celsius degrees. As you see, the agent could successfully learn how to keep the tank temperature above the comfort level of the people. And also the agent is overheating the tank at least once per day to make sure that Legionella would not grow in the tank. So we compared the performance of our reinforcement learning model with the conventional rule-based method, and we observed that the reinforcement learning model could provide around 24% of energy saving. It is always preserving the comfort of the people because in only less than 1% of the demands, the comfort temperature is violated, but the average of these violated temperatures is also 39.3, which is very close to the comfort temperature of 40 Celsius degrees. And also the agent could successfully respect the hygiene aspect of the tank because it has learned to overheat the tank at least once per day. So based on our results, we can conclude that a water heating system that can learn and predict our behavior is able to save significant energy without disturbing our comfort and health.
Thanks very much, Mireza, for the nice presentation, and also once again, congratulations for your success, not only with the research part, but also with the development of your innovation project that you do on the side, and that will continue, as I said, next year with as an ENAC Innovation Seed Grant. So we are very eager also to see this progress, and congratulate for the various initiatives you took for not only the research part, also the software and the hardware development. I think it's very exciting what you're doing, and very relevant, of course, to the topics of the Smart Living Lab. Unfortunately, unfortunately, no lunch today. So yeah, we will have to say goodbye on screen. Laura, maybe you can already say something about the program of the Smart Living Lunches of next year.
Continue with the Smart Living Lunch next year, about once a month. We have different format, let's say. You can also invite speakers from outside of the Smart Living Lab, the so-called invited talk. We have already one which is scheduled on the 15th of March with Kevin Hauser, who is doing research on daylight, and then I will send you some a doodle with some dates. You can just choose one slot and present the state of your research. It doesn't need to be completed. It's also a work in progress. We can exchange about your research in progress. So yeah, take the advantage, the opportunity to discuss your research with the Smart Living Lab community.
Yeah, I think one very positive aspect of doing it online is that we can have attendees from Lausanne and from beyond. So we both share between Smart Living Lab members here in Fribourg, which is the first purpose of our internal seminars, but also, and I think it's very important for all the researchers here to have also an audience beyond, and especially among the community at EPFL in Lausanne and on other campuses. Mireza, you do work with Sion, right? I don't know if anybody from Sion is in the audience today. But yeah, for those who are not familiar with it, I mean, EPFL has several campuses, Sion, Lausanne, Fribourg, also Geneva and Neuchâtel. And then, of course, the research community is all over the world. So it's great and when we do it online that we can have an audience that is also attending from international places. So I wish you all a nice end of year time, Christmas or whatever you celebrate, a good family time, and Happy New Year. So looking forward to meeting you for a successful 2022.
Thank you, Mireza. Bye, everyone.